of topic. We're going to go back to the title of the conference, Boom, and speak about supernovae. And the speaker is Tanner Murphy, who is a student here at University of Illinois with Brian Field, and currently at Stony Brook with Will Farr. Yes. I will give you a 5 minutes warning.
And take three. So my name is Tanner Murphy. I'm a master's student at Stony Brook University, but I did my undergraduate work here at the University of Illinois, where my focus was in near-Earth supernovae. And part of that work covered what I'm about to talk about today, which is supernovae in the Milky Way and being able to see them with LSST. So the question of the next supernova in the Milky Way is not one of if it ever happens, it's when it happens. A paper out of Ohio State by Scott Adams, and among others, back in 2013, estimated there are 3 to 4, plus or minus 2.5 per century in the Milky Way. Dust and among a bunch of other factors like the sun being in the way can account for why we haven't seen one since 1604. But even then, if it was still on the order of 3 per century, we should have seen them with neutrino detectors by now. Either way, when I'm referring to galactic supernovae, I'm referring to supernovae, like especially within the plane, which is what that diamond represents up in the top figure. And the histogram below shows that in the galactic plane, of the 295 galactic supernova remnants that are in David Green's catalog of galactic supernova remnants, there are, at least as of 2017, 273 of them are within this diamond, and therefore well within the plane where there's obviously a lot of dust and other stars and whatnot. And while it's not guaranteed that a galactic supernova will go off sometime in the lifespan of LSST, that's not exactly the point of scanning for galactic supernovae. The point is to get the progenitors of the supernovae, which since there isn't really any actual progenitor data on supernovae, because once one goes off, the progenitor's gone. No chance to get data on it again. So time series data leading up to the event would be invaluable. You'd have actual observational data that can be compared with simulations to see how well everything lines up going up, which could help with modeling these explosions. It'll also help with figuring out what exactly pre-supernova variables look like, with the fairly famous recent dimming and undimming of Betelgeuse, the Eta Carina, which is tearing itself apart right now, but again, and also distinguishing supernova imposters, like what happened with 2009 IP, where it wasn't exactly a supernova that we saw, but it was classified as one for quite a while. This mostly does only apply to core collapse supernovae, mostly because the progenitors of core collapse supernovae are obviously they're much easier to see. They're giant, massive, bright stars that stand out from the background. You can get it to work with the single degenerate case of type 1As, where it's a white dwarf feeding off of a very massive star. That's because you still need that very massive, big, bright star to be able to see it. double degenerate case of two white dwarfs merging would be next to impossible to distinguish from the background. So LSST in particular comes in with its IJ and K, or its IZ and Y bands, because a lot of the dust in the Milky Way is 35 magnitudes of extinction to the galactic center, just to there, from Earth. So there's no real way any telescope of any size can see through that in the V band. But in infrared bands, that's halved and up to halved especially for the Z and Y bands. So this graph here shows that the apparent magnitude of these stars and how different dust models count for it with these, in this case, atoms, which is the source of this figure, use a K band, which isn't quite what LSST has, but it's quite close. It shows that, especially with V band versus E band, as you get further and further along, it gets much, much better. The bottom figure in particular is the one that covers the progenitors, where even if you can see out to magnitude 25 of the V band, you still only get maybe 40% of the progenitors, where you get up to 100% if you look in the infrared. And again, iterating again, this is about core collapse and about the progenitors, because if it was searching for actual supernovae, especially for core collapse, we'd have the early warning system of neutrino detectors, and every telescope in the world that can see it, that won't be destroyed by looking at it, will be looking for this. So the LSST's importance really comes in with finding what it looks like beforehand, and the galactic plane that is covered by that diamond that I showed before only works out to about 8% of the sky, and the Adams paper claims that you only need to go past about once a month to get the data on that. Certain people, like in the previous talk, can argue for faster cadence, but this one doesn't nearly need as much rapid time devoted to it. And as far as other surveys compared to it, Assassin was modeled also in the same paper. It only sees about 32% of the core collapse progenitors, whereas LSST can see upwards of 2/3 of them, depending on various factors. But it always works out to LSST can see almost twice as many progenitors as Assassin and other surveys that can cover the galactic plane. And specifically for core collapse, it's 3. So sigma is almost mu. You take that as you will. 3 ± 2 per century. The famous case in 1987A, neutrinos can provide early warning detectors, where you get minutes to hours of heads up to point every telescope you have at it, but that still you only get those few minutes leading up to it. If you want much better clarity of what it looks like up to the explosion, you need time series data leading up to it. And this plot here shows roughly a combination of where they're distributed and how, with a bit of dust extinction involved. But that is, again, the diamond is the galactic plane, and pretty much all the probability of seeing a core collapse progenitor is within this plane itself. And a quick simulation shows that if you ignore the 66% from before, comes from also accounting for confusion from nearby bright sources, and if it's too bright to saturate the detectors. But at the very least, if you ignore that, you can get up to 75%. So again, the progenitors are likely extremely variable. Again, with the models of the instability from the shell burnings that are occurring, plus some observations of stars that are known progenitors like Betelgeuse. But in what way, how unstable do they get towards the end of their lives, and all that. you get. Then on a type 1a, they're more rare. You get 1.5 plus or minus 1 per century, and that's including both single degenerate and double degenerate cases. They are more dispersed they are more dispersed vertically due to the fact that when you have a star needing to go all the way to the white dwarf phase, at least one, you have much more heat dispersion vertically. But even then, it's still almost completely concentrated in this galactic plane. And with them, there's an 85% chance that the type 1a is bright enough because the progenitors are so far out, they can ignore a lot of the dust extinction that blocks the core collapse. Even though the infrared can cut through the dust a lot, it's still the easiest way is to just avoid it. Then touching on historic supernovae, where there's a lot going on in this plot. The things to note though is that all of the supernovae that have been seen by humans and recorded and localized have been viewed from the north, the global north. The yellow line in there is the global equator, and the furthest south you get is 1006, which was just barely above the horizon for many of the northern civilizations that would have seen it, but it was type 1a that was notably bright even for a type 1a. It was much brighter than Venus, and therefore nearly impossible to miss. But LSST being in the southern hemisphere can also help fill the gap of viewing that has resulted from every single one being easily visible from the northern hemisphere. And with the fact that there are only 6 in the last 1,000 years, continuous survey monitoring events that are as rare and hard to come by as supernovae that are in our own galaxy is obviously important. Quick talk.
You deprived me of the possibility of telling you 5 minutes because you were perfectly on time. Question?
Hey, very interesting talk. I just had a question about the progenitors of core collapse supernovae. I really did not understand why they are concentrated in the galactic plane as compared to 1A.
So that comes from the dust in the Milky Way, which makes the stars themselves and also blocks a lot of the light that we see, is very concentrated into a thin disk. And since core collapse are massive stars with very, very short lifetimes, they don't have enough time to disperse vertically at all before they explode.
More questions? Alex.
Hi, I'm Alex Kim, and the question is, would neutrino observatories benefit from having a kind of a short precompiled list of potential supernova progenitors so they can optimize their searches?
As far as I know, neutrino detectors don't really have a preferred direction, since neutrinos themselves are so unlikely to interact with whatever you put in front of them. They can kind of just tell what direction they're coming from based on, and it's sort of like they can see all directions at once. There's not really as much preference on direction.
We have a question online from Konsta. Konsta, can you unmute, or would you like me to read your question?
No, thank you. I'm okay after Alex's question.
So let me read the question, which was, what is the maximum distance we will see the neutrino signals from a galactic supernova?
What's the maximum distance we can see? So with neutrinos, you should be able to see them pretty much through the galaxy. They don't want to interact with, they're so difficult to interact with anything in the first place that they just pass right through more anything. With different bands, the V band visible spectrum will get about 2/3 of the way to the galactic center before it gets too extincted to see with anything. Infrared will get a bit beyond that, but still not all the way through the galaxy, but much further. And the key part is getting on the other side of the galaxy, because that means you have the entire area of where they're most likely to occur, which is towards the center.
Hi, this is Armin Rest. I think you overestimate a little bit the number of supernova per galaxy per 100 years. I think we are definitely overdue to have one in our galaxy, but with neutrinos as well as with looking at supernova remnants, we do know that they were not that. I mean, we don't have like 2 or 3 supernova per century. There is one supernova that is literally right through the galactic center, like a little bit off, and that was discovered with, I think, radio that is like about 100 years old, and that's the youngest supernova remnant that I think is known in our galaxy. But of course, with LSST, you're absolutely right. We will have the data to look for progenitors if a supernova goes off. And when you look back in the past with Kepler, Tycho, and Cas-A, we had like 3 in basically 1 century, and but then we had also, now we had like several hundred years with just one. But yeah, it's very interesting.
Thank you. Any other questions? There's one more on Zoom. Never mind. Gotham, did you have it?
So Tanner, always great to have an alum come back here. So welcome back. I am a little bit curious as to what we can do outside just the Milky Way, right? LSST is not just only looking at the plane of the galaxy. We have a bunch of nearby galaxies in the local universe where we will be able to resolve stars. So do you have any predictions for how many of these systems we could study overall in the LSST survey?
Not entirely, because all my research focused on the Milky Way, so I'm not aware of like how many of the nearby galaxies we can resolve stars. I'm assuming it also depends on where in the galaxies they are, because as you get closer to any of the galactic centers, it becomes harder, whereas you get further away, they can distinguish themselves more. So I'd have to run a little bit more on other galaxies and more code.
And I guess, can I quickly ask a follow-up? If we're looking for Cocolab's progenitors systems, it seems to me that you'd want to focus in on areas which have an excess of star formation, so maybe areas like spiral arms. Did you see anything in your study where there was any kind of difference in where in the galaxy?
It's not really a difference in where, because like I was saying to answer one of the earlier questions, the massive stars form in the region with a lot of dust, and they don't live long enough to move far away from that. The reason why there are these bumps further out is because you're looking more like you're looking through more of this ring area, but also there's just so much dust in the middle that even with the excess of star formation, it blocks it. And so it's really trying to find it's less about looking where they're absolutely more likely to occur and looking where you can find the balance between where they're most likely to occur and where dust and among other things, blocks it.
So any other question? We have time for one question. Otherwise, I'm going to ask you to tell me if I would characterize this correctly by saying that LSST has to change nothing to achieve this science. If a supernova goes off and it's visible based on the dust, we will definitely have information on the progenitor, which is great news, right?
Yeah.
Awesome. Oh, Gotham.
I'll just point out that if a supernova goes off and LSST is observing, we'll need to find a neutral density filter very, very quickly.
Awesome. I think this concludes this session, but we